Chapter 5, Torsion, Part B, A Deeper Understanding of Failure Patterns. A very common question in material properties is a question which one is ductile and which one is brittle and why. In chapter 3, we almost learned that this is a guess of a behavior of a ductile material, which we observed that in chapter 3. I will provide you with the link for that video. And that's because they have a kind of plasticity. It goes by necking, and that neckings all of a sudden goes by a failure. So that's a pattern of a ductile behavior of ductile material in axial force, and brittle material cannot handle tensile force, and they just goes by a 90 degrees to the axis of force, to the axis of force. So that's a tension, but that's the behavior of material in axial load. Let's let's see what so that's if you review the stress and strain diagram, sigma versus epsilon. This is the what happened in a brittle material. They just goes by almost a 90-degree to the axis of force, and the other part is a necking, the behavior of ductile material, which almost can simulate by a 45 degrees angle. But what we reviewed was so far about the axial force when a P tensile force applies to a ductile or brittle material. Let's go and see what happens in a torsional sample. So if we do have a circular shaft handling a torsional torque at both ends, and if we want to observe element A and element B, a circular shaft with stress elements at different orientation. So in this case, we do have only a shearing, and let's go by tau maximum because we want to observe the maximum effect of shear. And a random sample of B just goes by both of them. Mhm. Let's consider a shaft element mhm, with only shearing stress and normal stress. So let's study an element with just element A just goes by pure shear, and element C goes by just 40, just a normal stress. How that goes? So if we take out a sample of 45 degrees, mhm, that's the case of only having a normal stress on that. Let's see how we can approach the problem. So again, if we want have two sample in torsion, two element in a torsional sample, one of them just goes by pure shear and the other just by normal stress. So if we just take an element out and goes by a summation of forces in n direction, and n is just a 45 degrees angle from the horizon. So in that case, F minus, let's translate this is tau maximum in, and if we call this area A naught, that's tau maximum A naught. A translation of that in 45 degrees is tau maximum A naught cosine of 45 degrees, because this is 45, this is 45, this is 45. F should be cancelled out by the opposing force at the minus F direction. So F minus 2 of tau maximum times A naught times cosine of 45 goes 0. That says F is equal to 2 tau maximum times area A naught times cosine of 45. And if you do the mass, it gives you tau maximum A naught square root of 2. And then just normal stress, because we are looking for normal stress in our element. That's simply F over area. We reach to, we calculate F is tau maximum A naught square root of 2. And if we call this part A naught, that's a translation in hypotenuse, and that's A naught times square root of 2. And that's just, let's cancel out A naught, square root, and that gives you, wow, that's interesting. If we have tau max, sigma maximum is exactly tau max, but that's sigma. But in such case, in a way that we have two elements, the one has only pure shear by the amount of tau maximum, and the other with a 45 degrees, which sigma normal is exactly tau maximum in a torsional shaft. Mhm. Let's go a bit deeper and see shear failure of a shaft subject to a torsional torque of T. If you remember from previous section, which is axial load, if you remember, we just observed the element in axial load, which just goes by a, happen to handle a tensile force. It just goes by a necking. And if we want to simulate that necking, that's a simulation of almost 45 degrees. So one can say ductile material generally fails in shear. So when a tensile force applies, the plane of rupture or fracture is almost a 45. So they are more, the plane of rupture is almost a shear. Likewise, so if we want to see the same effect in our torsional sample, so this is a torsional sample, let's go by the element which has the shearing stress under. So this is element A, which just goes by pure shear. And if you closely observe the shear with respect to the sample, it's just perpendicular to our sample. So one can say a translation of a shear failure in a torsional sample. So this is a torsional sample, mhm, handling torsion of T. In a ductile failure for torsion is a parallel to the sample. So that's a representation of a ductile failure um, for a ductile behavior in a torsional sample. Likewise, if you again remember what happened in a sample in tension for a brittle material, they cannot handle a tensile force, and they just goes by a almost 90 degrees to the axis of forces. So that says brittle material are weaker in tension. If we want to translate the same behavior in a torsional sample, that's a brittle material weak in tension, and that's sample element C is only handling a pure normal force, that's a tension. And that in that case, in such case, you can easily see this is the angle to the vertical, that's 45 degrees. And if you observe the material, you can easily see how they just goes by a almost 45-degree to vertical line. That's the sample of failure. That's a behavior of brittle material in a torsional sample. If we want to wrap up the uh, material and have a clear conclusion from that, one can say a ductile material in a tension when happen to handle a tensile force at both ends just goes by necking, and that's getting narrower and narrower until the plane of shear is almost 45 degrees, and that's a representation of 45 degrees fracture plane. Likewise, from previous slide, we just learned that a ductile material, when happen to handle a torsional torque, just goes by a 90 degrees to the axis of the material. So that's 90 degrees. Mhm. Likewise, in brittle material are weak in tension. So if we apply a tensile force, they just goes by a 90 degrees to the axis of force because they are weak in tension, and that's a simulation of that. And also, uh, likewise, if a brittle material happen to handle a torsional torque, goes by a 45 degrees, which we observed in previous slide, and that's the sample of a shear plane of shear for a brittle material. So, as a conclusion, it's a pretty interesting fact that says a ductile material in tension acts exactly like a brittle material in torsion. Mhm. Goes by a 45 degrees in plane of rupture. And likewise, a brittle material, a brittle material in tension, mhm, which goes by a 90 degrees, exact like a ductile material in torsion. So the answer to the very first question is which one is ductile and which one is a brittle. It's the what is the uh, it depends on your force. If you are applying a tensile force, there is there is it's a situation one, and if you applying a torsional torque, it's a different story. So you have to observe your condition of force, then answer the question. So if that's a torsional torque or a axial force. Thank you.